Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today is the 16th video in the Advent of Code series, where I do about an hour of Advent of Code per day, unless I really feel like I can finish it soon, and then I push on a little bit longer, but in general I try and limit myself, which is why we're still on day 13. So in the last video, I started day 13, completed part 1 with a fairly simple brute force solution, got to part 2 and realized that it would take a lot more to finish. So if we take a look at the code, we started to try to optimize it, and we figured out that instead of using a nested for loop, we could have one for loop, and within that for loop, we could do some maths to figure out whether the other button would be able to fill in the missing target value. So that basically means instead of a nested for loop where it's iterating once and within that iteration iterating again, we're just doing one iteration with a single check per time, which would massively increase the speed. However, it doesn't increase the speed enough, and in fact we're still getting an overflow issue. So let's run this here. And we still got print statements in from the attempt to figure out what's going wrong. Actually, it looks like we're not overflowing just yet, so maybe that is fixed. So what I'm going to do today is what I thought we could continue doing yesterday, but we ran out of time, which is instead of doing a straight iteration, we're going to implement a binary search. So in case you don't know what that is when you take an upper and lower bound that you need to search between, and instead of checking every single value from the bottom to the top, you take the middle value. Is the answer higher or lower? If it's higher, you then take half the upper value. If it's lower, you take half the lower value. And you keep repeating that and getting closer and closer and closer until you hit the right answer. Now, I'm expecting that to be log 2 of the number of checks. So let's say we were doing 1.2 billion numbers. We then, by doing the log base 2 of 1.2 billion. So you go, instead of doing 1.2 billion checks, we'd be doing 30, which is going to be much, much, much faster. So let's implement that. But before we do, I'm a little unhappy that we have two functions, one called min_tokens and one called min_tokens corrected targets, and we have essentially the same algorithm with minor differences inside it. So the first thing I'm going to do in this video is to collect those together into the same algorithm before then improving it to use a binary search. So let's begin. Okay, so I'm going to add two parameters to the min_tokens function. Now, Rust doesn't have a way of doing let's just stop this running. It doesn't have a way of doing named parameters, like let's say Python. So if I wanted to run a min_tokens function in Python, I could leave these arguments blank, or I could specify target adjust equals something, or max iters equals something, which means that in Python I only have to put in the arguments I care about. There's no way to do that in Rust. There might be some workarounds, some ways to make it look neat, but I'm not interested in pursuing that right now. I want to do the challenge. If you do know of a way to do that and you'd like to suggest it, please put it in the comments. So let's take our min_tokens. We are going to start by calculating the target x. Now for this, our target adjust is 1 trillion, I think I said it was. So we're just going to change that to be target adjust. Great. Now, we're going to replace self.targetX with target X and self.targetY with target Y. And now when we call this function for part A, we are going to give it a target adjust of 0. And the max iters, we're going to give a sum of sum of 100. Actually, we'll give it a sum of 200. That's what we were doing before. Okay. So by doing that, instead of going, we have this running from 0 to min iters, we're going to be changing that. So firstly, we have our minimum iterations. We also want to have our maximum iterations, and I'm editing the wrong function. We want to have our maximum iterations. So if max iters dot is none, then we need to calculate it. Actually, instead of doing that, I can create and go straight to the next step, which is I want 2 mutable variables. One to be the lower bound, which will start off as min iters, and one to be the upper bound, which is going to be max iters if it exists, or okay, or 0, error 0. I want to give it unwrap or, yeah. Unwrap or, and then if it's unwrap or, I want to calculate the max iters. So I'm pretty sure that I can give it a function here to correct the right thing. Unwrap or else, which lets me pass in a function. So for this, I'm going to give it an empty closure because I don't want to pass it anything. And I'm going to paste this code in. Okay, so at this point, I wanted to tab in, but tab instead exited the auto-generated code. So at this point, upper bound will be max iters if a max iters was given. If not, it will calculate the maximum iterations based on the parameters that are present and then return that instead. So now we only need one function. We don't need min tokens corrected target at all. We can delete that, and where it was previously called, we can now give 1 trillion. That's a million, billion, a trillion. And it will be none for the, and we correct the function name. There we go. So we expected U128 and we found a usize. Let's go ahead and make that a U128 then, and fix anything within the function that gets upset about that. U128. Okay, that looks like it's working. This isn't happy because it's giving an option of U128, and it doesn't know. Part A is returning a usize. We can make that a U128 as well. Okay, great. So now we want to correct these test functions. We're going to take part A and part B. That's fine. For this, we're testing. It will be 0 and some 200, and it will be 1. Oh, can autocomplete that and pass none. I can also do named functions that pass these parameters for me so that they have better names, but I think because I'm only using them once in real code and once each in the tests, that I'm not going to do that. But it would be pretty easy to do if we wanted to. Okay, let's stop here and do a cargo test, make sure that everything is passing. It is not passing. Ah, yeah, of course, because we don't actually have a correct answer for one of these. Increase target single machine and part B both fail because the puzzle text didn't give us the correct answer for these. So we're not actually sure what the correct answer is, which is why they're failing. The important thing for these is that we make something run. Okay, let's start working on this binary search. So I'm going to start by writing a loop which says do this forever. So it's a keyword that creates an infinite loop very simply, but we can break out of it if a certain condition happens. I may rewrite this to a while loop if there's a good exit condition, but this is a good way of doing a do while, basically. Okay, so we're going to take a test value that is halfway between the upper and lower bound. That will be the lower bound plus upper bound minus lower bound over 2. So let's say we're testing between 10 and 20 button pushes. 20 minus 10 is 10, divided by 2 is 5. 10 plus 5 is 15. 15 is halfway between 10 and 20. Now, we can already check whether our test value is okay. Let's say we're checking the lower bound is 10 and the upper bound is 11. We would want that, in that case, it will be the lower bound. Actually, I'll look more into the termination condition, but I think this will be check test val against upper bound for termination condition. I believe this will just be if test val is equal to upper bound break. In fact, we can just straight up return a number, and the number that we've got, we can calculate it. So but we're not storing it anywhere. Okay, I will come back to this. I'm going to leave this commented out for now, and I'll come back to this. So we can now say our remaining x. In fact, we can copy a lot of this. So we want to check our remaining x. If our remaining x modulo by our x value is not 0, meaning that we have missed the target, then we need to figure out if it's too high or too low, right? So let's think about this some more. If our target is 100, we're doing, we wouldn't do 11 rolls of max by x. We'd do, say, 9 rolls. So if it is if remaining x is lower than, we're checking it against the min by x. So what happens here? If it is not possible with min by x, then we need to figure out whether to check the upper or the lower bound. So we would either set the upper bound to the test value or the lower bound to the test value. But which we set it to is the important part of this algorithm right here. So I'm going to rename this to button pushes to make it a little more obvious what it's meant to represent, rather than test val. So we know it is at minimum 10 button pushes. We know it is at maximum 20 button pushes. So we're testing 15 button pushes. Now, if we exactly hit if remaining x modulo min by x dot x is 0, meaning that, oh right, yeah, I'm doing that. I need to check y as well, that's the thing. So if it's not 0, that means that we can't hit the target with that test value. Now, if at this point the value is... Actually, we don't really have a too high or a too low here. I think that's what's confusing me. We don't know whether to go up or down. So if we're trying to reach 8400, we know that the maximum is 8400 over 94. We know that the minimum is 8400 over 22. Let's quickly figure out what those are. Ooh. Apparently I don't have Python 3 installed. Python. 8400 over 94 would be 89. Min is 89. And the maximum is over 22. Now in this case we've picked quite a good test case because the x value gives the maximum and minimum iterations. So it'd be 381. Remember, when you do an integer division, it will truncate. So it doesn't round, it just removes the decimal part. Okay, so for this, we're trying to go between 89 and 381. So we'll do 81 minus 381 minus 89 is 292. 292 over 2 is 146, and 89 plus 146 is 235. So for this iteration, button pushes is 235. Now if we do 235 times the maximum, which is 94, then we get 22090. The remaining is, wow, we're already well beyond. So yeah, we are too high, basically. This button push won't work. We need to get so that the button pushes is below the target x. Yeah, that is true because we never get negative numbers. Wait, so is this even true? Minimum iterations to maximum iterations. 8400 divided by 89. 8400 over 94. We need... That's the maximum value. The maximum value it could be is, let's say it's all button pushes of B, because that's the smallest value that will go up to it, right? So in that case, our maximum is 381. So that is correct. The minimum is if repeatedly pressing button A exactly fits into 8400. So that would be 89. So yeah, that is right. So I think we need to get to a point where, yeah, we can discount a number if we can discount a test value, a button pushes value, if multiplying it by the upper gives us way too much. But if our minimum, so we can't go below 89 because then it is impossible to reach the value. If we press our biggest button that many times, we can't reach it. So yes, we do have to go halfway between. So at this point, it's too high, so we have to go in between the two. So we're going to reset our upper bound to 235. Becomes 235. Then we repeat the algorithm, right? So then it's 235 minus 89, 146 over 2. Add on to 89. 89 plus 73 is 162. Okay, so now button pushes is 162. 162 multiplied by 94 is 15066. So again, we're too high. So upper bound becomes 162. Then 162 minus 89, 73 over 2. 89 plus 36 is 125. Buttons is 125. 125 multiplied by 94 is 11750. Why do I get the feeling that yes, what I've done makes it so that the minimum, what I specified as the minimum, is the most that, if you multiply the minimum by the biggest number, it will exactly reach or just under reach the target you're trying to reach. So that just isn't true. The minimum is 0, really. So all of this algorithm doesn't make any sense. So let's try doing it like that instead. Okay, so our maximum is 381. So we're going to divide by 2, which is 190. So we're going to start with buttons at 190. Now you've already seen from what I was just doing that 190 is too large, so we can immediately set the upper bound. Upper equals 190. Then we can do it again. So 190 over 2 is 95. 95 times 94, still too large. So then if buttons is 95, then upper becomes 95. Now we're actually in the region that it needs to be. In fact, maybe we need to be multiplying by the lower number in order to reach a target. Okay, so I might be doing it a little bit wrong here. Let's continue this and see if it finds an answer. So, upper is 95, which is too much, so that means we need to find a new button value. 95 over 2, 47. Buttons is 47. Maybe that's what it is. Instead of going from 0 to 381, we're going from 0 to 8400 over 94. So we can binary search between 0 and 89. Right? So that makes this algorithm, what I've done so far, a bit wrong. But let's delete this and start again. So it is 89 over 2 is 44.5. So buttons is 44. That means that our value is 44 times 94, which is 4136. 4136. So 8400 minus 4136. 4264 modulo the other value, 22, is 18. So it's not that, right? But we don't know whether to go up or down from here. Yeah, so I'm not sure we can binary search this. We don't know whether to go up or down. Means all of this is wrong. Yeah, because it can be any amount of either one. So we can't say that. Okay, I was really sure that I could binary search, but I guess I didn't think all the way through it. I don't think there's any way of doing it because we just don't know whether our candidate number produces a result that is higher or lower. There's two variables to try and fit into the target. We almost want to search two numbers at once. Is that possible? Because we're testing each number, right? So we start at we start 89, we multiply by 94, and we check whether we can get the value from that. We calculate remaining x. We check whether remaining x is divisible by the other x. If it is, we check y. If they're both divisible, then we check how many of the B button pushes it took, and then do the A button pushes plus the B button pushes as U128. Yeah, I don't think that this helps. We don't even get anything from max itters here. And then if we cargo run, oh, I got a number. I don't know what I changed. I don't need to know the maximum iterations. I can calculate it. Almost immediately comes up with an answer. I don't know what I was doing wrong before. If that's not the right answer. Okay, so that's wrong anyway. So what did I do that made it work that out so quickly? I guess we need to go up to max itters. Okay, let's put max itters back in. And then we're going to go up to max itters. Is it min itters to max itters? Instead of thinking too hard, I can just test it. 0 to max itters. So min itters doesn't do anything. And then at this point, okay, so this is where it's going wrong. Somewhere between 0 and max itters is the right answer, but we can't add it on. So I think we need a big, a num big int. All right, let's try using this. So we're going to cargo add num big int. I think it was big int. No, yeah, big int. Okay, and then we're going to use num big int. Yeah, big int double colon. Rust Analyzer is struggling because it's having to now compile it, so it's big uint. We're going to take our big uint, and we are going to, here we are, we've got big uint imported, and now we can start to actually use it. We are returning an option of big uint, so I would assume that we can convert to it, or do we need to do big uint from? Let's try from as a number. We can't convert from i64, but we can convert from u128. So let's just convert all of this as u128. Now, I think we should probably make all of these u128 as much as possible. I'm not sure if we ever need the negative number. So we're just going to directly do that. This needs to sum, but we can't sum across big integers. So what we can do here is return a big uint and another big uint. I can sum across big uints. So I think what I want to do is I'm just going to copy and paste these because I want to have the debug form in case I need it. But basically what I want to do is down to dot sum. So is that, yes, that needs another bracket, and then that's okay. And then I can do the same down here, except that it will be a different target adjust, and it will require none as the upper bound. There we go. Okay, so because Rust automatically initializes 480 as an I32, I'm specifying U32 for it. That's a way to construct numbers. And again for these, I'll do big uint double colon from 280 U32. Oops, I've already done cargo add. Let's do a cargo test, which compiles all the numbers, and it does not compile. I'm not sure why not. I'm just going to close this and reopen, and then rerun it, which shouldn't make a difference, but I may not have saved, and it didn't make a difference. Source main RS sets at 54. Aha! Okay, so there was a reason that these were signed instead of unsigned. So what I'm going to do is reset them back to signed. Have I already done that? Have I gone too far? I did go too far. I'm going to redo everything and then undo again until I get... You know what? I think I'll just keep all the redos, and I'm going to change these to I64s, and then I'll go through and correct all the compile errors as they happen. Target adjust and max iters will be I64s as well. I think that's it. And then, okay. We've got 2 passed, 2 failed, and the 2 that failed are the part B ones. Okay, so let's do a cargo run and see if we get an overflow. Okay, unfortunately, that is still taking a long time. So let's see if we can figure out what the issue is. So one thought that occurs is that the puzzle states that the maximum number of any button to be pushed is 100. So instead of having max pushes, we could have a max pushes per button, and then we would actually be able to use this minimum. And I think that would roughly halve the surface area we're looking at. So, you know, we're dividing by 2, but we don't want to divide by 2. We want to do a lot better than that. So I think this does require some more thought. A different algorithm, a different way of searching. What would be great is if we didn't have to iterate at all. From max iters down to 0 is what we're currently doing. From min iters is wrong. It can be somewhere in between. But ideally what we'd like is some way of saying better bounds, or a better way of searching the space for the right number of iterations. It's a bit of a shame that we're not using this min iters at all. Okay, I think I'm just going to be quiet while I think about this some more, and I'll cut to if I come up with something. Okay, one thought that occurs is that I'm not sure why it needs to be max iters rather than min iters. Okay, so the space that I need to search, but let's assume, so I don't need to worry about which is actually the bigger or not. Let's assume that A is bigger and B is smaller, which is the case for this test.txt. So we're going to bring this back in. So in this case, the area that I'm searching is between 8400 over 22, right? Which is 381. Well, I guess it'd be 382. We should probably add 1 for the max. And then the min on A, min from A is 8400 over 94. So 89. We'd want to take the lower bound from that one so that we're searching from the min to the max. So given that what we're actually searching is from 0 to 89 on A, and here I've calculated that max is B, right? So we're currently calculating from 382 down to 0, all inclusive. That doesn't make sense. That's like quadrupling our search space. So we want to go from 0 to 89 on A, where for each one up to 382 rolls pushes on B, right? So realistically, this should be min. I don't understand why that doesn't work. Let's remove the part B tests. And cargo test. Let's try and set that space down. Oh, that does work. Does it? Yeah. Okay. So that means that we want to take... Well, it doesn't really matter about the max iterations. I'm pretty sure I've already tried this answer and it was wrong. It's not the right answer. Yes, it's too low. Which implies that it's not finding some possible solutions, right? Let me just write this is too low. Now what we could do is just literally add 1. Which gives us another possible answer. What happens if we add 2? This is 1305. Keep that in mind. Oh, okay, that's the same answer. So I think this might have just been an off by 1 error. Let's see what the answer is. See if this is the right answer, rather. That is too recent. Oh, when I saw the 2 lines of text, that's what you normally see when it was successful. Let's try again. I think it's been about 8 seconds. Nope, the answer is too low. Okay, this is made very difficult by not actually knowing what the right answer, even for a small input, is. I might double check that that is actually correct. Turn to day 13, go to part B. Okay. That's interesting. I'm adding the wrong number. That's really sad, but let's change part B so that it actually uses the right number. So this should actually be 10 trillion, not 1 trillion, 10 trillion. I should have double checked that a long time ago. Let's cargo run that. Which unfortunately increases the space to search yet again, but now we have another new answer. Let's check it. That's not the right answer. But it doesn't say whether it's too low or too high. That is a problem. I mean, well, I don't know if target adjust fits within an i64. It should. An i64 is huge. Let's convert this to U128 just to make sure. Okay, now we need to convert these and these. All right, I'm just struggling with the type conversions here. Okay, so i64 to a U128 where N is an i64. That's an i64. Only M is i64. Let's convert this whole lot into an i64. That should fit. That makes M an i64, and then this whole lot can be converted to a U128. And then we can return some big uint from total cost. Okay. I don't know what difference that made, but we can run this and see if we get a different answer now. The end in is a different answer again. Why is this now a different answer? It's slightly bigger. I mean, I'll try it. I'll try it. It's not the right answer again. Okay, I can't check my answers anymore because I have to wait 5 minutes between each successive input. It would have been nice if they could have removed that restriction for this particular puzzle, given that they didn't give us a right answer to check against. I wonder if I've done my logic wrong in the maximum and minimum iterators. So what's 5400 over 34? And over 67. So it's got to be the maximum of the two minimums, which I've got. And therefore the minimum of the two maximums, right? Yes. Yeah, that's right. But I wonder if that's even right at all. Well, the minimum from B is lower. Minimum from B is actually 80. Not from B, from the Y. Which means that I'm actually going from 0 to 80 on A. Because... is that right? No, because I'm taking the maximum. Yeah, that is the maximum, so it is 89. So that's right. I think I need to start looking for hints here, but I'm gonna continue on for a little bit and try and figure it out. So the thing is, we do get a reasonably fast answer, it's just not correct. And I wonder if that's because we're missing possible solutions. So if we're going from 89 on A down to 0, maybe, let's say there's a solution at 88A and at 40A pushes, right? So we'd find the solution at 88 first, and we'd stop. But what if the A token cost is 3, so it's 88 times 3 plus a few times 1, let's say 12. And the 40A would be 40 times 3 plus, I don't know, 100 times 1. The point is, we've not necessarily found the minimum number of tokens. We might have had a solution which has multiple possible solutions, which means that we shouldn't go we shouldn't just immediately return, basically. We should keep a hash set of our solutions. Okay, so what I'm doing is, instead of immediately returning, as soon as I find one solution, I search the entire space for all the solutions and then take the minimum that I get from it. So let's try that. That did give me something different. I have reduced my score. So where is it here? Here we go. How does it compare? Very slightly different, very slightly lower. But I think it's probably been 5 minutes, so let's give it a try. It's not the right answer again. I mean, that did change it, but at this point I don't know if I'm just doing something wrong because of my Type conversions. I think I need to not add one. And then if I do that, it will never overflow, and I can just keep everything as U128. Let's try it. Do I get yet another different answer? Yes, I do. And I can't check it because it's too soon after the last one. I mean, we should no longer have any conversion issues, right? Let's tidy all this up to just directly use U128. Unwrap or else. This will be so. Like that. Remove the as U128. Remove the as U128. I'm not even using it, that's the funny part. Move as U128. See if I get another answer. No, it's the same answer. That's somewhat reassuring. So I think I'm going to try and put it into the puzzle solution box. And when it tells me that I've not waited 5 minutes, I'm going to find someone else's solution online and give it a go. So we're going to have Reddit day. This is 13. Solution. Advent of code. And of code. So I don't want to look at how they're doing it. I just want to run their code and get the answer. Language Go, Python, this seems good. Let's grab all this and dump it into here. I'm not reading it. I'm gonna save this as a stolen solution.py. And then I want to run it. So then can I run Python source / stolen solution? And I don't actually know how they get the puzzle input. Sys.stdin.read. Where does it do that? Sys. I guess I can cat the file into it. I may have to change this so that it does it. So with open /puzzle / input.txt as f, contents is f.read lines. The machine in contents. It wants read. Okay, try that. I am currently in this directory, so I don't need to do ... I just run it like that. Okay, this is the right answer. So I am way off. I'm now just reading the solution. What is div mod? This is the parsing code. Prize x, prize y, ax, ay, bx, by. Is it this simple? So this is a cost of 0. If there's any remainder, you need to multiply I don't know how I could have got this. Okay, so I am over time here. What I'm gonna do is I'm gonna convert this into Rust. And then I'm gonna try and understand it. And then once that's done, we'll stop with day 13. I think basically there's just some clever mathematics that I didn't figure out. I'd like to understand it, but I don't think I would have come up with it, even if I'd spent several more hours on it. So congratulations to those people who did find the right answer here. It's just not something I thought of. So let's we actually don't need, I don't think we need any of this. I think even this would fit in an i64. So I'm just going to convert everything back to i64s. I'm going to get rid of this big uint. And every time I see big uint, I'm going to change it back to an i64. If i64 is not big enough, then I will change it to an i128. So option i64, here we go. So going to do, yeah, it is literally these lines of code. So let b multiplied is ay times target x minus y. Y times target x minus self.a.x times target y. That b divisor is self.a.y times self.b.x minus self.a.x times self.b.y. That a multiplier, the a multiplied is target x subtract self.b, b times bx. Oh, so I need the result of a division from before to be able to do this. Okay. So I'm just going to use their b and b rem. Let b equals b multiplied divided by b divisor. Let b rem is b multiplied mod b divisor. Then I can have a multiplied is minus b times self.b.x. Let a divisor equals self.a.x. Okay, return if, oh, I need to actually do the division. Let a equals a multiplied divided by a divisor. Let a rem is a multiplied div a divisor. Then we can do if a rem greater than 0 or b rem is greater than 0, return 0. Otherwise, we return a times 3 plus b, also known as self.a.cost plus b times self.b.cost. This is actually none, and this is actually sum. If I cargo test, I get a failure, yeah, and if I cargo run, I get a different answer. That doesn't seem right, so I assume I am overflowing somewhere. 5128. 5128. Let's try that. I'll go run. Do now get the right answer? No. No, we don't. Why do we not get the right answer? So I'm getting that it ends in 105, but I know from their correct solution that it ends in 868. This is the parsing code, which should be fine, right? Because we've got the answer to part A. Let's double check these equations. So it's y times target x, subtract ax times target y, that's right. Divisor is ay times bx minus ax times by, yep. Then we do divide and mod. A multiplied is target x minus b times bx. Divisor is ax. A multiplied divided, a rem, a multiplied mod. If a rem greater 0 or b rem greater 0, return none. Otherwise, return sum and add everything on. I'm still getting my answer ending in 105. I mean, I'm allowed to make a guess. Imagine if I've just put the numbers wrong into this correct solution. So I'm calculating the wrong thing with their correct solution. That'd be interesting. But no, that's the wrong answer. Now I have to wait 5 minutes before being able to try another one. I guess what's better is to check their solution rather than my solution, but now I can't do that for 5 minutes. Okay, so when I do this, target x is self.target x plus target adjust. Can I do it for a single input? Let's just do test.text. I can at least compare that. Python. Helps if I change mine to do the same thing. Okay, so it's the same for test text. But different for the full input. But I feel like all I've done is copy them. Let's check the part 1 result. You answered yeah. So they've got that right. Let's check mine. This is now wrong. Okay. Something has gone wrong there. Now my part A code should call it with target adjust 0, yes. This does mean I'm not actually sure anymore if I've got the right machines, right? Well, I don't need to do this. I can just so I'm not sure my input is correct anymore, despite having got the right solution before. So let's print that out and do some checking. Actually, let's just separate it by line. For machine in arcade.machines. I think I can just borrow this. Print line machine. Cargo run. Okay. And then there's a lot of them. Let's open up input.txt. So it is 38, 33, 77. Oh, 1147. Yeah. And target 14612.879. Yes. Let's check the last one. The last one is 1977, 44, 19, 344, 1908. Okay, so something could have gone wrong in the middle. Seems really unlikely. It seems that I'm just calculating it wrong, even though I've copied their solution. So maybe at this point, it's doing the wrong thing. So let's convert these to big ints. Let target x equals self dot target x big int from self dot target x. Plus target adjust. Self dot target y, same thing. Target y plus target adjust. Be multiplied. Now becomes a big int. We get lots of big ints. Well, this isn't big int, so let's. The important thing is that the multiplied ones are big ints. Found integer, yeah. So this should be a big int from. And this should be a big int from. And then I want to return. I can return a big int. Why not? Okay. Use of moved value. Yep. Clone. Why not? Well, technically I can do it here and then it's okay. Target X is first used here, so I clone it. A multiplied is first used here, so I clone it. Then B is first used here, so I clone it. And then it's okay. Okay, I want to return a big int from here and from here. What do I get? 105. What do they get? Not 105. I literally don't know why this isn't working. Looks like I'm finding solutions for ones that the Python version doesn't find them for. I've already checked that one and it was the same. $121 0, $121 a value. Okay, so immediately this is wrong. Correct. So my AREM, my B, BREM, A, and AREM are all correct. Is my if condition wrong? Return 0 if AREM or BREM. If AREM is not 0, then we get 0. Cargo run, Python run. Okay, so it was my if condition that was wrong because the numbers could be negative. Can I do this without big ints now? Can I do it with i64s everywhere? That would be nice. Not necessary, just I want to pack it down to a slightly smaller number if I can. Okay, we no longer want big int from. Don't need these print lines anymore. Away they go, and then run. And then I think I'm still printing out my arcade, so I can remove that. Gone. Okay. Okay, that gives me the right answer. Now, I don't feel like I've solved this because I took someone else's solution. That's -1 for me, I guess. But it's not about solving it as well. The purpose of doing this is to learn. And in this case, there was a very simple solution. If only I was able to work it out. And I knew there was some possible maths that could do this, but I just didn't think to write it like this. So let's take a look. What it's essentially saying is px is equal to some number a times ax plus some number b times bx. At the same time, py is equal to some number a times ay plus some number b times by. Those are our simultaneous equations. And then we can just isolate for B and for A, right? So let's try and get A on both sides to begin with. Actually, what they've done is gotten B on both sides to begin with. So let's copy that. Let's copy that. Okay, so we're going to say that B times Bx is equal to Px divided by A times Ax. At the same time, B times By is equal to Py divided by A times Ay. So that's just actually that's not true. It's subtract. So Px minus Aax, Py minus Aay. Now for both of these we can take the lot and divide by Bx, and in this case by By. Now we have two solutions for B. But they both depend on this unknown A. So, okay, so I think what they did was actually solve for A first. So what they did was A is equal to Py minus B times By divided by A times Ay. And then same thing except with x's instead of y's. Right? And then they inserted that into B. So B is actually wait, this isn't right. This should be no, that's not right. It's Ax and Ay. That's right. So for this equation, we can do Ax. Now the Ax and this will be in brackets, right? So we're taking this equation and the Ax and the divide by Ax cancel out. Now B refers to itself, which is a bit interesting. So I guess we have to rearrange it for that. B times Bx is equal to Px minus that's too many brackets now. Px minus B times Bx. This is getting confusing. I think what I'm going to do is I'm going to watch a video or look at some explanations of how this works. And then I'll be satisfied that day 13 is complete. It is complete having used someone else's solution. So I will link the Reddit post to the day 13 solutions. This is the first puzzle I've had to take a solution to figure it out. I think this actually would have been a really interesting puzzle had I realized that I could do it using simultaneous equations instead of programming. But that's I64 from, how odd. I don't need to do this. Yeah, it would have been interesting had I gone with that, but I went too deep into the programming solution, ended up not finding a way to do it. So I think in future, if I come across a problem that involves, well, they all involve mathematics to some extent, but this was a set of simultaneous equations had I seen that, and I could have sat and tried to figure it out on paper. So going forwards, I'm going to look for those puzzles that have simultaneous equations or any other mathematical constructs I can see, and just practice trying to solve those using maths instead of using programming. With that, I'll end the video. I'll see you for tomorrow's video where we'll start day 14, and we'll see if that involves just as much mathematics as day 13 did. Thanks for watching, and I'll see you then.